consider a function that is both, let's say, continuous, okay, on the interval a, b, including a and b, and f is differentiable on the open interval a, b. Okay, so these are our opening criterion for two theorems. Now, let's just discuss these for a moment. So, what does it mean, and what's the difference between including and not including the points in the interval? Well, let's talk first about the inclusion and exclusion of points in the interval. So for a function to be differentiable, think of the limits. The limits have to get closer and closer to a value, but it doesn't actually have to hit that value, right? And that's why it's an open interval. Whereas for continuity, we need, for it to be continuous, it's got to hit the actual point. You know, just to give you an idea, like if you have a point here, like say here's A, and then here's B, well, that's not continuous at the end point, even though it's differentiable everywhere. So this would be not continuous. And what's an example of an A to B that would be not differentiable? Okay, well, any absolute value. Okay, so if this is our A to B, then it's like this is the absolute value of x. It's not differentiable. And the reason why it's not differentiable is because you have this corner here. Okay, so this is the absolute value of x. And if you have a corner, you have two different derivatives, two different slopes approaching that point, so it's not differentiable at that point in the middle. Okay, these are two examples of functions that contradict this statement, these two statements. So when we're looking at these two statements, we want a nice smooth continuous function without any sharp corners. Okay? We'll go ahead and take these off. Now, what are we looking at if we have these? Okay, well, we have a couple of different theorems. And for the first one, we're going to say, 1, if f of a equals f of b, then what do we have? Okay, this is interesting. There exists a c in the interval ab such that what? F prime of c is going to be 0. Okay? And this is called Rawls' theorem. Okay, so let's put up a visual of Rawls' theorem so you can get an idea of why it's true. Okay, so f of a equals f of b on a continuous differentiable interval. So you've got some, some graph here, and, it could be anywhere, right? But if this is f of a, then f of b has to be the same level to it. Okay, so you've got some function. Now it's got to start up or down. And let's just say it starts up. Okay, so it's up. It has to come back down to eventually get to f of b. It's continuous. You can't start here and cut back up. At some point, you've got to go down. You could go down many times. But note that if you go down at some point, what Rawls' theorem states is that somewhere on this curve, you must have f, there's got to be a c in between them, such that f prime of c is 0. Okay, where you have a horizontal asymptote. That is Rawls' theorem. Okay, kind of cool. Now, there is another version, and you could say, a deeper version of Rawls' theorem. It's not actually Rawls' theorem, but if we change number 1 to number 2, simply put, okay, there exists a C in AB such that, what do we have? What we have is that the derivative, okay, oh, and these should actually be open, not closed, but f prime of c equals f of b minus f of a all over b minus a. Okay, what's going on here? Well, this is very famous. This is the mean value theorem, okay, MVT, mean value theorem, and let's put up a second visual to better understand it. Okay, so for a second visual here, okay, we've got another plot, and now we're not requiring, f of a doesn't have to equal f of b, so it could be like up here. And what is this f of b minus f of a over b minus a? That's the slope, okay? That is the slope between these 2 points. And so what the mean value theorem says, if you go on some wild journey to get from one point to the other, somewhere along the way, you've got to hit that exact slope. Okay, you could think of it as like Rolle's theorem rotated, right? So if you take Rolle's theorem and you rotate it, right, then what that's saying is the slope between the 2 points, here it's 0, rotated, here it's f of b minus f of a over b minus a, that if you start up at some point, you got to come back and, you're going to have somewhere along here, potentially in multiple places, you're going to have a slope that equals f prime of c, the derivative equals the slope between the 2 points. Okay, that's the mean value theorem. These theorems are used a lot in proofs, I can tell you. And what I wrote up here is actually true, okay? Yeah, but it's stronger to say, oh, and it's like excluding the points A and B. So let's just write this up properly. Okay, it's important that you're aware of the difference in the notations. Okay, so there exists a C in A comma B such that f of B minus f of a over b minus a equals f prime of c. And same thing here. Let's change these to open intervals. Okay, so you want to pay attention to your open and closed interval. It's a stronger statement to have the open interval because it's saying we're not even counting a and b. There's got to be something strictly in between them. Okay, so what's an interesting example that we could consider looking at Rolle's theorem and the mean value theorem? Okay, well, how about the following? What if we have, let's do an example, okay? So let's say that f of x equals, now we're going to go with the cosine of x plus 3x. And what we want to do is we want to verify that f is only one root. Only one. Okay, so how do we go about doing this? This is actually an intermediate value theorem problem to show that it has a root, okay? And so recall how to do that. We need to find, first of all, let's maybe start. Okay, so we could start with basically f is continuous and differentiable, right? We know what the derivative is, we know that it's continuous, and this is important because we need this to kind of proceed with Rolle's theorem, the mean value theorem, and the intermediate value theorem, which is what we're going to use here. The intermediate value theorem, recall, basically tells you that, hey, look, if you have a negative and a positive, and it's continuous between them, then there has to be at least one root. Okay? So all we need is a positive and a negative f. And we've got to think about what we can put in to get that. And you know, when you're dealing with trig functions, it can be nice to kind of make them go to 0. So note that basically f of pi over 2 equals cosine pi over 2 is 0, 3 pi over 2, which is greater than 0, and f of negative pi over 2 similarly, because the cosine of negative pi over 2 is 0, will give us negative 3 pi over 2. And that's less than 0. And so by the intermediate value theorem, what it tells us, okay, there must be some number. There must be a c in the interval. Now we chose pi over 2 and negative pi over 2. Okay? So between pi over 2, negative pi over 2 and positive pi over 2, such that what? Such that f of c equals 0, and that establishes that we have one root. Okay, so how do we show there's only one root? Okay, there's a little trick here, and it's actually to use Rolle's theorem. So if you know what theorem to use, you can try to, in fact, apply it, right? So we've got that f of c equals 0, and now what we're going to do, let's look at the criterion for Rolle's theorem. It says if f of a equals f of b. Okay, so we're going to assume that there's another one. So we're going to assume that f of b also equals 0. Okay, so we have f of c equals f of b here. And then by Rolle's, and also we have that it's continuous and differentiable. So by Rolle's theorem, we have what? We have, there must exist a c and a and b. Now we changed the variables around. We've got a c and a b, but not an a here. Okay, so trying to get too confused. And so I'll say that there exists, just a variable change. There exists an a in the interval cb, such that f prime of a equals 0. Okay, this all seems fine so far, so let's check f prime of a. And so for f prime of a, what do we get? Okay, derivative of cosine is sine, plug it in and we get a. Sine of a plus 3. Okay? So, what? The sine of a is between 1 and negative 1, no matter what you put in. And so because sine of a is between negative 1 and 1, what we have here is that this must be always greater than 0, which is a contradiction. And the contradiction is from our assumption that there is a second root. Okay, so that in effect proves that there is one and only one root. Okay, just to give you one more example that's kind of fun and interesting. This applies, so, okay, example. So someone is they're traveling, okay. Their average velocity, let's just say it's, well, what did they do? They went 240 miles in 4 hours, okay? 240 miles per hour in 4 hours. And what that tells us is their average velocity would be 60. But the average velocity, okay, so, which is 60, right? Because you just divide. So 60, let's just write this all up. Average velocity equals 60, which is what? It's, say, s of b minus s of a over b minus a at two different time points, okay? Now, can you prove that the person had to be going 60 miles per hour at some point on the trip? Okay, this seems obvious, right? If your average is 60, how could you avoid going 60? Right? It would be like if you never got to 60, you couldn't go 240 miles per hour in 4 hours. And because velocity is continuous in effect, it's not like you can jump from 59 to 61. You can prove it, the fact that it's differentiable in a continuous function, using the mean value theorem. It must be the case that S prime of c, which is the instantaneous velocity, instantaneous velocity, it must equal 60 at some point. It must equal 60 at some point, say, by the mean value theorem. Okay, so I just think this is another cool example of using the mean value theorem to directly apply to something that we all know. Other problems that you might see things like, for what values of c will these theorems apply? And what you typically do there is, you would basically take the derivative of some function that you're given, like this one. You set it equal to this. You would have the original function, they'd give you an a and b, and you plug it in, and then you would solve those for c, okay? And so that's another standard example. It's important to know Rolle's theorem, the mean value theorem. I really think it's nice to look at the mean value theorem as a rotated version of Rolle's theorem. So then Rolle's theorem too, you've got f of a, the slope from like f of b minus f of a is just 0 because they're equal. Okay, so it really is a rotated version of that. And you will see the mean value theorem come up in some different places, so try to remember to use the mean value theorem, you have to be continuous and differentiable. Continuity includes the endpoints a and b, differentiability does not. And then there must exist a c within the interval. It's true, it's within the bracketed interval like I had, but even better than that, it's got to be strictly between a and b, not including a and b. And then it's f prime of c equals f of b minus f of a over b minus a. Great theorem, used to prove a lot in calculus. That's the mean value theorem.